Welcome everyone to another interesting DSA problem. The title of this particular problem statement is maximum depth of binary tree. So we will try to explain what is the problem statement. You will be given a binary tree. We have to know or access what is the maximum depth. For example, if this is the given root node, okay, as we go deep into the root node, like this is the level 1, this is the level 2, and this is the level 3. So as you can see, the depth is nothing but 3. So we have to return this number. So how can we do that? One thing we can do is that we can use a recursive method. So it's better to explain. First let's write the code, then we can see how this particular code functions. And it's already given the constructor of the binary tree here, and let's explain the code part. So this is a class definition and all, class solution. This is the method, define maximum depth. Self, and which is given is root. Root is nothing but an optional tree node. And we have to return an integer, that is nothing but the depth. And first we are going to write down the base case. The base case is nothing but if not root. If the root is none, that is you can return like this, if not root, we have to return 0. Return 0. So this is the base case. Let's write it as base case. And we have to use one variable, left depth, which is nothing but we are going to call the function again, self dot maximum depth root dot left, and right depth is nothing but self dot maximum depth root dot right. We will see how this is working very fine. Then at the end we just need to return 1 plus each time when these two things get executed, then we have to check, we have to return actually 1 plus 1 addition to maximum among the left depth and right depth. Let's see how it works. We will go one by one. So this is the given example, okay, and root is given. Initially it is here, and we are going to check the base condition. If not root, yes, root exists, so this particular thing will be skipped. And the next thing going to check, or we going to call, is left depth. We are going to assign left depth to calling that function, and the function inside that argument is set root dot left. So the root here, the argument from here to jump to here, okay. Then the control sequence is here, right now it's here, okay. Then again we will check if not root, yes, there exists this thing, so this again will be skipped, and it's going to check, it's going to access left depth is equal to root dot left, so it will go here. Here it is actually none. So in this condition you can see this particular base case will be executed and it will return 0. That means at this time the left depth will be assigned a value of 0. Then it control sequence will go to here. Right depth is equal to root dot right. This will also be checked. This is also none. So here also the base case get executed, and here write depth would be assigned as 0. And we at this point we are going to return 1 plus maximum of 1 plus maximum mm, left depth which is 0 and right depth is equal to 0. That is nothing but 1. 1 will be returned. So here in this particular case, for example, if you go into, we have to write down the stack. You can see how it is going to work. Okay, maybe not stack, we can see how it is working. So 3, when the node 3 called, when the node 3 has been called, then it takes the control sequence to 9, and from 9 there is none and none. So here it becomes 1. So we will again go back to here, the 3's right depth. This is 3's left depth. I am going to note it as left depth LD. This is LD, this is right depth. Okay, and for 3 also there is right depth. Okay, that will take us to 20, and the 20 will have a left depth. Okay, that is nothing but 15, and the 15 will have none, and right depth also have none. So this will both return 0, and the return will become 1, and we'll again come back to the 20th right depth has 7 has none, another none, so this will give 1. And if you see this one and this one, maximum among these two is 1. So this will return 1 plus maximum of 1 comma 1. So this will give you a sequence of 2 here. And again we are going to use something known as, this is return 1 plus maximum of 2 comma 1. That is nothing but 1 plus 2, which is nothing but 3. So this is how the recursion is going to work here. So intuitively this is going to happen. So it will go up to deep and it will clear back and forth. So this is going to happen. And the question is, what is the time complexity? So the time complexity, in a worst case, like it's a skewed tree, just like a linked list, if something like that, worst case, like not, it's like time complexity to the order of n. And what is the, no, basically time complexity irrespective of what is the nature of the tree, it is order of n. But the space complexity, based on the skewed nature, or it can, like if it's skewed, like based on like a linked list, if it's something like linked list, it would go up to order of n. But if it's a balanced tree, for example, it's equally spread out, we don't need to like store many of the things at a time. In that case, like balanced tree, the space complexity would be log n. So this is the time and space complexity. So time complexity order of n, because we will be visiting every node at least once. That's why. And I hope you understood this problem and its particular solution. Thank you for listening.